yeah, theoretical roles of duality. What do we mean by that? And it's the roles of duality that are closely tied to satisfying the schema, so to what is the definition of duality. And so that is mostly related to the questions of theoretical equivalence and empirical equivalence and inequivalence. So what we discussed yesterday, the past 2 days, remember the bearing of dualities on the questions of formal conditions for two models to be theoretical equivalent, but also we discussed that there are interpretative conditions for models to be theoretically equivalent. And so these are the two questions we're going to be looking at today, after looking at the examples yesterday. And in particular, I will also focus on the question of empirical underdetermination, because that's one of the natural questions, also one of the old philosophical questions that philosophers have been asking before actually dualities became a big topic in physics. And so it would be very interesting if dualities had something to say about this whole philosophical topic, which in fact goes back to, of course, Poincaré, but even earlier, the discussions between Newton and Leibniz and so on. So I will say more about that later. Here is the outline. So 4 points: theoretical equivalence in philosophy of science. What do we mean by that? Duality and theoretical equivalence. So what does duality, can duality have any specific contribution to theoretical equivalence? Then epistemic issues about theoretical equivalence, because one of the things I would like to emphasize is that when we talk about theoretical equivalence, we shouldn't only think about it in terms of either the formal schema or the interpretative part, but also there are epistemic issues that we need to address. And then fourth, under those issues, the question of underdetermination, duality, and scientific realism. So we begin with theoretical equivalence in philosophy of science. And just to remind ourselves of how we have viewed theories for many times, and of course there are various traditions, but one well-known way to look at the theory is as a set of sentences. And in addition, an interpretation that assigns reference or items in the world to those sentences. Alternatively, we can look at the theory in semantic terms as a set of models or structures. And I should emphasize that during the first part of my talk, I will use model in the traditional sense, so not in the sense that I defined in the first lecture. I will come back to that sense in the second part. Okay, so the traditional criterion of equivalence in this tradition is, of course, logical equivalence, but it has been argued by many people that this criterion is too strong. In particular, logical equivalence requires two theories to be formulated using the same signature, same vocabulary. And so if we formulate Newton's laws as F is n times A using the dot, or we formulate them as G is n times B, where instead of using a dot, we use a star, then this should not count as a difference. And yet, the strict criterion of logical equivalence would tell us that it is. And so, therefore, it has been very natural, and this is a very old topic, to look for suitable translations between theories. So Quine and Glimmer in the philosophy of science started programs for this. Glimmer's criterion of intertranslatability. So for Glimmer, two theories are intertranslatable if they have a common definitional extension. So if they have definitional extensions that make them logically equivalent. So the criterion is still logical equivalence, but now not applied to the original theories, but rather applied to two new theories that you can get from the old ones by adding new definitions. And you add those new definitions such that you can make these theories logically equivalent. So here is on the slide we have the technical definition as This has been studied and revised recently by Barrett and Halvorson. Thank you. And they have proven a number of theorems about this. I will not go into the details, but just to illustrate how Barrett and Halvorson make this criterion precise. They do this in first order logic, but I'm a physicist, so at least by training. So I will try to, I'm going to give an example that is closer to physics, which is the isomorphism between U1 and SO2. Of course, a very simple example, but still non-trivial. So consider U1 defined as the set of numbers on the complex plane that satisfy this condition. Here U star equals 1. And then on the other hand, SO2 as the 2x2 matrices with integer entries that satisfy this usual condition. Now these two groups are isomorphic as groups, but they are, if we would write them in a formal language, they would not be logically equivalent because their models are not the same. They have different models. The models of U1 are numbers in the unit circle on the complex plane. The models of SO2 are 2x2 matrices of a certain form, and obviously a number is not a 2x2 matrix. So that very simple realization leads us to then try out this idea of enlarging the theory. So I have written here the signatures that we use. So the symbol I for writing a number on the complex plane, and then the multiplication, and then on the other hand for SO2, the notation we use for the matrices, and then for taking absolute numbers and then the multiplication. So here is the so here is the definitional extension that you could write to translate one theory into the other. This is again following Barrett and Halvorson. So you add to U1, you add to SO2 basically the symbol I and also the multiplication. So you do that by making this correspondence between a complex number written as U1 plus IU2 with this matrix over here with the same numbers U1 and U2. And then likewise for the star, for the complex conjugation of complex numbers, where we now flip the sign basically on the off diagonal. Okay, so adding these definitions, the signature of SO2 gives us a signature that encompasses the two theories, the signatures of the two theories. And we can also do the same on the other side. For U1, we can add to it the relevant definitions that allow us to formulate things, sentences using the signature of SO2. So we define again what is a 2x2 matrix by giving basically the converse of the previous, and then we define matrix transposition, which we need here in our definition of SO2, and then also we define the matrix multiplication, which we have here in terms of addition of complex numbers in the exponential, or alternatively we could do that in terms of U. So that's almost obvious. And then doing this, we can enlarge our two theories, and they are logically equivalent. Now their models are the same because any model U, that a complex space that we can write as a complex number on the unit plane in T1, gives through these added definitions. So by adding these definitions, that number is now has a definition in terms, basically gives us a model of T1, so a model of SO2. and like was in the other direction. So the procedure is symmetric. And so T1 and T2 have a common definition of extension. So through this kind of procedure, what we see is that, well, the natural notion of isomorphism that we would expect for U1 and SO2 in mathematics, if we had a formal language for this example, we could make that precise using definitional extension, and then we get the equivalence we want. So this is basically the program of Barrett and Halvorson. They contrast this with another criterion that Quine introduced in a well-known paper in '75. His well-known paper where he introduces, one of the papers where he talks about underdetermination. So his criterion of theoretical equivalence is that rather than adding new definitions to basically make to change the theory, to make a more general theory or a theory that has bigger signature, rather he introduced what he calls a reconstrual, which is rather a map from one theory to the other. So two theory formulations express the same theory if they are empirically equivalent, and if there is a reconstrual of predicates that transforms the one theory into a logical equivalent of the other. So I won't go into the details. Again, Barrett and Halvorson formalize this in first order logic. So they show how you can actually make these mappings. But they notice that this criteria is too weak because, and the problem is basically that it is not symmetric like Glimmer's criterion was. This counts as theoretically equivalent theories that one does not expect to count as equivalent. So for example, they argue that it can, and they give a very simple example that you can map an incomplete theory into a complete theory. So basically they compare two theories of which one has slightly more, has more sentences, and then you can map one into the other by forgetting that additional sentence. And you can do that because you don't need inverse map in Quine's criteria. So they say, well, that is not good. That is not what we expect. But then they strengthen the criterion, so they basically add the other direction, and then they obtain a criterion that they call Quine intertranslatability. So if you strengthen the criterion, then you get a criterion for which they prove a theorem about first order logic to the effect that if two theories are Glimmer intertranslatable, then they are also Quine intertranslatable. And they also prove a theorem about the converse. So if the signatures for the two theories are different, then the converse is also true. Okay, what I want to here, the idea of these slides is just to give you a flavor of what has been the discussion in the philosophical literature in the past few years. And I'm sure that some of you have followed this, at least some of this discussion. There have been other developments on category theoretic criteria. So a number of authors have proposed category theoretic criteria. For example, Halvorson and Sementis, they propose a syntactic category where the objects are sentences and the arrows are entailment relations. Also, Weatherall has his own proposal, semantic category where the objects are modes of the theory and the arrows are homomorphisms between them. He illustrates this for general relativity and also for the Maxwell theory. And then there are various functors between the categories that play various roles, such as forgetting in essential structure. So also Weatherall has this notion that when you have what I call two modes of theory, there is some structure, and they are in some sense equivalent, then normally they differ in some structure that is not common to them. And so this is what I call, or what we call, the additional structure, while Weatherall formalized that in terms of a particular factor, and then illustrates that in an example.
I haven't read Weatherall. Could you say a couple of words about how he treats Maxwell theory? Or
yeah. What he does is he takes two different formulations. So he takes the formulation with the Faraday tensor and the formulation with the electrical magnetic fields. So the electrical magnetic fields, they don't use the gauge field, it's just the fields themselves that you measure, while the Faraday tensor utilizes more structure, uses the gauge field. And so he says there is a gauge symmetry in there, and then you have this forgetful functor that basically gets rid of this additional structure.
Thanks.
Okay, so two comments on these previous criteria, and this is where I have, well, I'm going to connect with the work that I am doing and my own view on this. So we have seen that we have two kinds of requirements for theoretical equivalence, and we have the formal requirement, but we also have the interpretative or semantic requirement. By formal, I here simply mean mathematical. And the previous criteria have focused on finding an appropriate formal or mathematical framework for theoretical, which certainly is a requirement. It's something you need. One remark that I have on the category of theory frameworks that I have seen so far in this recent literature, in the way this discussion has developed, is that they tend to be too general, to give a top-down criterion that reproduces the kinds of verdicts that one expects in physics. I should say Weatherall's criteria are the ones that come closest to that. But what we see in those category criteria is that we find a variety of category criteria in the various papers by the different people. Within a given paper, you will find 3, 4, 5 or more different criteria, and that is all good. That's all in the game, and we might be able to do better in the future. We might be able to find more refined criteria that do reproduce the relevant physics. But for example, the types of categories in the physics literature, there is also quite a bit of discussion of categories, for example, in the context of quantum field theories, especially modular tensor categories are discussed in conformal field theory and in topological quantum field theory, three-dimensional Chern-Simons theory, and also Q deformations of two-dimensional Yang-Mills theory. But those haven't been really discussed in the philosophical literature. So my point with respect to the applications of category theory in the philosophical literatures, on the one hand, they're very general because they are purely top-down, but they usually are not able to make the connection with with modern physics, basically, except in some examples. So things like conformal field theory, quantum field theory, non-perturbative aspects of quantum field theory, and so on. So that's why I think that a more bottom-up approach, as far as a philosophy of science is concerned, of course, we have, on the one hand, we could have the formal logical project, but I am engaged here with a philosophy of science project. So from that perspective, the bottom-up approach seems much more fruitful. So to begin from the examples where we know what the equivalence is, and then to build from there, basically. To use the categories, for example, that one or the kinds of equivalences that one finds in the examples. That's one remark about the general formal or mathematical project that we are engaged in. And then the second remark is that the second criterion of semantic or interpretative equivalence is seldom addressed in this more formal mathematical literature. And one could see maybe reasons why, because of course, semantics and interpretation is difficult to formalize. It also depends on all sorts of things, like it's content dependent, it could even be theory dependent, depending on what scientific theory we are discussing and so on. Nevertheless, there is quite a lot of knowledge among physicists, and also philosophers have quite a few general things to say about interpretation and about semantics of scientific theories. So it's worth taking that on board in that interpretative project. So that's why I think that the bottom-up project that combines the two aspects is a very fruitful approach. So to begin from the examples that basically physics and other sciences give us, and also from the kinds of questions about interpretations that arise already in philosophy of science. So that's what I will try to do in the rest of the talk. And then, of course, here I'm going to advertise our own, I mean, it's not ours, but the duality criterion as a formal criterion that is very natural, because it is an isomorphism criterion. Now, an isomorphism is always defined relative to a previously defined structure, and we know that it has been a very successful criterion, not just in physics, but in all of science. And so any formal criterion, it's basically a criterion that is normally used in physics for equivalence, and also in other fields that can be formalized or semi-formalized, where in any case mathematics and formal methods can be applied. And so any relevant criterion that claims to be more general or more precise, but still relevant for physics, will have to reproduce the isomorphism criterion in the examples, because in the end, that's the criterion that works in physics.
Do you intend isomorphism about the theory, or isomorphism about the structure, the models?
It depends what you mean by models in this case. If you use my language from the first day, then it would be isomorphism between models.
Models yeah. Intended as the most simple representation of physical systems.
Yeah. But here in this first part, I'm reverting to the traditional philosophical jargon of theories and models. That's why I'm for the time being, I'm talking about theories or theory formulations. Later on, I will revert to my usage from the other day. Yes, that's what we need. Okay. So that's the formal proposal that isomorphism is a good criterion, and then we need to be able to reproduce that criterion in the examples. And so now what remains to be discussed is the part that has been less emphasized in the past recent years in the literature that I just discussed, which is the interpretative aspects. In particular, interpretative aspects of theoretical equivalence. So, okay, and now is where I revert indeed to the use of models that I defined in the first day. So the question is, are dual models in our sense automatically theoretically equivalent? The answer is almost obvious, no. for the reasons mentioned, because duality is a formal criterion, it's a mathematical criterion, but it is not, therefore it's not guaranteed that the interpretations are the same. And so this is in part also why duality is useful. It relates models that we would not expect that should be related, but they are related. So regardless of interpretation, duality gives us interesting relations between models, and thereby we can find new things about the interpretation. So the interpretations need not be fixed when you begin working with dualities. Examples of this is, for example, Carmen's Vannier dualities, and Jeremy will emphasize this on Friday, where we have a lattice at low temperature versus high temperature. According to the normal interpretations, those are obviously not theoretically equivalent. Those are obviously different interpretations, different physical situations. If you put a thermometer there, it will give a different different number for the temperature. And the same for other examples that we have seen. Now here is where I think there is an interesting distinction that one should make before proceeding, which is between internal and external interpretations. And here the formal steps of the schema come in handy. Because the previous discussion relied on knowing already beforehand what the interpretation of the model is. When I say high temperature versus low temperature is different, I assume that I already know what temperature is. But and the same for elementary bosons or elementary Fermi expansion. So this is what we call an external interpretation. Those are the normal interpretations that we usually work with in science interpretation that have been developed sometimes throughout a long period of time using empirical data and so on. So those are the external interpretations. Now, I would like to mention a related notion, which is but a different notion of interpretation, which is an internal interpretation. So the question is, what if we do not assume that we can always interpret theories independently of dualities? So what if in our interpretative project, we take dualities into account? So if duality is going to be input for how we interpret our theories, just like other formal aspects are also input for what we interpret as a degree of freedom, for example, then we would be cautious about interpreting the specific structure, because after all, we have two models that we know are isomorphic, but they don't share some structure. So, so that's the starting point for the internal interpretation. Basically, an internal interpretation is an interpretation where you don't interpret the specific structure, where you say, okay, I have an isomorphism, I'm only going to interpret that part of the structure, that part of the models that is common to the two models, that is preserved by the isomorphism. And the specific structure I'm going to, for the time being, at least, disregard. So that's what we call an internal interpretation. It is, it shouldn't be so surprising because, like I emphasized, we do this all the time in any interpretative project. It is never the case that we just develop interpretations just by sheer thinking or in some a priori way. We always take into account what are the formal requirements of a theory. For example, what is the kinematics of the theory, what is the dynamics, what are the different degrees of freedom, what are the symmetries, and so on. So we always naturally do that. So now that we also have this new formal notion of duality, which we hadn't encountered before, I would say that we are at least, if not compelled, then there is a strong forced to take the duality into account in our interpretative project. It's certainly an important formal input that we should take into account. Okay, so what I've just mentioned of taking two models and basically disregarding the specific structure and only interpreting the common structure, that you could say it's a process of abstraction, right? You go from two models that have a lot of structure, but some structure that is not shared. We go to a more general model of which these are representations. So that model is more abstract. It's like when we begin from models of a group, and then we try to build an abstract definition of that group. That's a process of abstraction. The other day, so yesterday, we saw in the example of bosonization that that is not the only thing that we do when we develop an internal interpretation, because sometimes the duality prompts us to a new discovery about things that were not in our external interpretations. For example, when we said we have a bosonic model, but now duality tells us that there is an operator, e to the power I phi. This operator is a fermionic operator when properly normally ordered. That's an operator that is there in the theory, it's allowed by the theory, but it was not part of our external interpretation, because we didn't consider it to be a physical operator, because we thought we were dealing with a bosonic theory. So now the duality prompts us not just to drop some structure, but also to add some structure, namely to promote this specific operator that is allowed by the calculus of the theory, to promote it to a physical operator, to something that should have a physical interpretation under an internal interpretation. So internal interpretations are not just about common structure or abstract, or I should say, are not just about abstraction, but they can also be about augmenting the structure of the theory. Okay. So therefore, we have two interpretative cases. We have the usual case of distinct but isomorphic sectors of reality, where we have two different interpretations, for example, two external interpretations that disagree with each other. In that case, the theories are theoretically inequivalent. But of course, that doesn't forbid the other sort of case that we are after, where we have two theories that are theoretically equivalent, so they describe the same sector of reality. And this is what is modeled by the internal interpretation. And I have modeled it in this diagram over here. We have here for the states, for the quantities, the set of quantities Q for the two models, and then we have two interpretations into the world, I1 and I2. They describe the same sector of reality. So we can write this as this commuting diagram as basically the commutation of the interpretation map with the duality. So I will say that interpretation commutes with duality as an image. I will use. So this is a case when duality allows us to give a verdict of theoretical equivalence, namely if we adopt an internal interpretation. Okay, so that's basically the notion or the formulation of theoretical equivalence that I'm going to use. So two things: we have a duality, and we have an interpretation map that commutes with the duality map. And in particular, I have argued that an internal interpretation does precisely that. So that is a sufficient condition. On that side. So yeah.
Sebastian, can you repeat the last part because I
Yeah.
am not completely clear.
So the last part is basically that if we want theoretical equivalence, then we want to have this commuting diagram. So we have the two models, but we have one domain of application. And so the two maps, the two interpretation maps, they have the same codomain. And so the condition that we get is this commuting diagram is that the internal interpretation that it commutes with the duality map.
So there is isomorphism, but the two structure would be not models of the same theory.
No, they're still models of the same theory because we do have a duality. So we have a duality between them. So you could say there is still a theory above which these are representations. But that's the formal side. So in addition to that formal side, I'm looking at the interpretations on how this maps to the world, to how this maps to a domain of application. And then there I get an additional condition, which is that the duality map needs to commute with the interpretation map.
Okay.
And that's my formalization for what it means to be theoretically. Yeah. Okay. Very good. So now we are going to the epistemic issues, which I would say, have been addressed even less, or although they have been started to be addressed in a number of papers that I will also discuss. So a number of important papers by several philosophers. Okay, so far I have described the formal side, and I now just told you something about the semantics, what kind of semantics we want. Well, we need to make this distinction between internal and external interpretations. We also have this meshing condition between the duality map and the interpretation map. And now epistemic questions. Some of these have been addressed very recently. So one of them is, when are we justified in adopting an internal interpretation? That is one of the questions that I would like to address. And the other one is whether dualities bear on the question of scientific realism. That is, of course, a very natural question that we would want to ask. Let me see, how are we doing with time? We have until. Okay, it's until 6:45, right? We started 4:45. Yes, very good. Okay, so here again, I'm going to address the first question. Let's consider how we justify our interpretations of theories and how we do things like have debates about scientific realism. Now, one obvious way in which an internal interpretation can be limited is if it only gives a partial interpretation of the world, so of a small or limited domain. So that could limit the application of the kind of interpretation that we have. And so that would mean that while the models are theoretical equivalent on a smaller domain, they might turn out to be theoretically inequivalent on a bigger domain. So that's something to keep in mind. Most of our theories, all our theories have limited domains. And so we need to say something about those kinds of extensions. In many cases, this is made explicit by physicists when they tell us that we are dealing with an effective theory, when they tell us that the domain of application is limited in some sort of way, for example, because there are corrections, there are quantum corrections, or there are other sorts of corrections. So in such cases, it is good epistemic practice to extend the theory to a larger domain of application and to adopt only interpretations in the smaller domain that are consistent with this extension. So this is something that physicists do all the time? Will the interpretation that I am having today, will it still be consistent tomorrow for the same theory? Well, if there is a larger domain, what do I need to say? And of course, we cannot look into the future. But that's not that, we don't need to do that either. But we do need to think about ways in which theories can be extended. So two jointly sufficient conditions for duality that lead to physical equivalence are therefore as follows. So one I call an extendability, which is that each dual is about the whole world, so it cannot be extended beyond its domain of application. Symmetry principles often help here in the sense that if you know what are the defining symmetry principles of the theory, sometimes you can limit the kinds of possible worlds that you could have. So some of these yesterday, the cases where we said, okay, we have these non-perturbative states. We cannot handle them in a practical way in our theory, but we do know that they exist, and we know them from the very definition of the theory. The very definition, namely the supersymmetry algebra, which is the part of the definition of the theory, tells us that such states should exist. So whatever interpretation we have for this theory, it will have to be consistent with the existence of those states. So that's one way in which sometimes you can make those kinds of restrictions of the domain. Also, for example, in limiting the number of dimensions, usually you say, well, how do I know the dimensionality of the world? Well, I don't really know how many dimensions the world has. It appears to have 4, but maybe it has 5. It's an empirical matter. But in some theories, like for example, string theory, the number of dimensions could be fixed, and it's in fact fixed by symmetry principles again. So these kinds of symmetry principles, if they are strong enough, they sometimes limit the domain of application. Again, what is needed here is not so much that you can say that, okay, this is going to be a theory of the whole world or something like that, or the only possible world, or something of that kind. But rather what we need to be able to say is that that theory will be robust against extension. So even if I discover a successor of this theory, if it is a successor that is compatible with my definition, for example, compatible with my symmetries, then that kind of definition will not change. This is sometimes the case for effective theories as well, where we say, well, quantum field theory is an effective theory. It could be limited up to a certain scale, a certain cutoff. But if my theory is Lorentz invariant, then automatically I can exclude certain kinds of particles. And so certain kinds of extensions will not be possible. And so certain parts of the interpretation will be robust against those extensions. Okay, so that's the first kind of sufficient condition that I think warrants talking about duality leading to physical equivalence. If you adopt an internal interpretation that is an extendable, then we are warranted to say that these two theories are physical equivalent. The other sufficient condition, and actually you need both conditions, is what I call defining domains, which is something actually quite simple, which is that now we need to, in addition to saying what is my domain, we also need to specify what is the equivalence that we have. So we need to make the ontological commitments explicit. So we need to specify what kind of entities there are in the domain. Let me say a bit more about the need for an extendable theories. And this ties into some recent work by Reed and Müller-Nielsen. So they observe that an explication of a shared ontology of two models need not exist. And this is what they call motivationalism. So they say, well, sometimes theories simply don't have good interpretations. And so before you commit yourself to saying that these two models are theoretically equivalent, you should have their common ontology already at hand. This is the argument. So I agree in this in the sense that, for example, when we deal with inconsistent theories that make predictions that are in some sense mathematically inconsistent, that limits automatically the domain of application of that theory, and that runs counter against these sufficient conditions that we've had here. So I agree with so this is a concrete, I would say, a concrete instantiation of that idea of Reed and Müller-Nielsen. So dualities then give us an interesting distinction, or rather, I should say that the distinction that we have made for the interpretation of duality apparently gives us two different kinds of dualities. On the one hand, we have extendable theories where the verdict of physical equivalence is quite limited by the fact that we have these extensions that may lead us to change the interpretation of the theory. And on the other hand, we have unextendable theories where the verdict is not limited in this way, because we know that our interpretation will be, or we have a good argument that our interpretation will be robust against those extensions. And so an example of that is some quantum field theories, including bosonization, and possibly string dualities are of that kind. Now I would like to go in more detail into the actual position by Reed and Müller-Nielsen, which they have also defended not just for dualities, but also for symmetries. So they defend a motivationalist approach to dualities, according to which the existence of duality-related models first, and this is their language, motivates us to provide an explication of the shared ontology of these models. Okay, so the existence of dualities motivates us to look for an explication for an explication of the shared ontology, but we will only have such an explication once we interpret these models as representing the same possible world. So A, excuse me, A implies that the decision to interpret duality-related models as being theoretically equivalent needs to wait upon an explication of their shared ontology. So in the way they frame the dialectic of this argument is that, well, we are first motivated to take this first step of looking for this explication of this shared ontology, but the interpretation can only be had once the actual explication is there. So that is motivation, what they call motivationalism. And they contrast that with a position that they call interpretation. So I argue that the motivationalist position is close to my own position that I expressed earlier in terms of defining domains. So if we claim that models are theoretically equivalent, then we need to make our ontological commitments explicit. That's what I said before. In other words, we have to work out what is the common ontological picture. So that is close to motivationalism, but there are some differences, and they are really minor. So one difference is that I don't think that holding that dual modes are theoretically equivalent is tied to a scientific realist position as they do. So part of their argument is framed in the language. It assumes a scientific realist position. I don't think that's necessary for us to talk about theoretical equivalence, because we know that, for example, philosophers like Reichenbach also defended his own kind of theoretical equivalence position. So that is certainly not necessary. The anti-realists can also hold modes to be theoretically equivalent, even if they have semantics that most people nowadays would not agree with. So in my view, the position is best formulated not in terms of the attitudes or activities of epistemic agents, as Reid and Müller and Nielsen formulated, but rather in terms of the epistemic justification of the claim of theoretical equivalence. So that's just a minor difference, I think. So I take a more neutral stance here. I prefer to, I think it does more justice to what we are talking about, to think of it in terms of epistemic justification. It basically brings it closer to the science and closer to the discussion about scientific realism and the kind of evidence that we have for the claims of theoretical equivalence. Okay, and then the third point is just again a very minor point about how these steps these methodological steps are taken. So I will skip that in the interest of time. Okay, so now we have discussed well some of the epistemic positions that we have, the epistemic justification that we have to make claims about theoretical equivalence, and I have given you two jointly sufficient conditions, namely an extendability and extending domains. And then I went into Reid and Müller-Nielsen motivationalist position. I emphasized that it is really rather close to their position with some minor differences. Now I would like to go into the discussion that I announced before of underdetermination and scientific realism. And here I want to discuss something that I call a cautious scientific realism. And at the outset, I would like to say it is not a new brand of scientific realism. I mean, there are I don't know how many types of scientific realism out there. And this is not a new type in that sense. It is not, but rather it's a methodology that I would like to introduce for how to construct scientific realist position. So the question is, before we get there, is do dualities give cases of empirical underdetermination? I think that's a very natural question to ask. And Dean Rickles in, I believe it was 2013, and also Keizo Matsubara, they were some of the first philosophers to write about dualities. They already, this was one of the first questions they mentioned. This is an important question also from the philosophical perspective, because it has been quite controversial whether there are actual cases, good cases, in philosophy of science of what we call empirical underdetermination. Quine himself thought that this was an open question. So in his paper on underdetermination, he goes through a series of reformulations of the underdetermination thesis, and he says, well, it is really an open question whether there are actual cases of underdetermination. And that has been an open question ever since. And the best cases that we know are some of the ones due to, that is also Van Frassen have discussed, But as Larry Loudon and others have criticized, these are almost always involved or related to the relativity of motion. So they always in some way or other involve that fact that we can describe things using different frameworks of reference. So if dualities gave us a whole new class of examples of underdetermination, of empirical underdetermination, that would be quite nice. Or if not, lacking that, then it might give us some other insight about the possibilities for underdetermination. So in particular, the question will be, do dualities give the anti-realist new ammunition? Now, I will anticipate my answer, which will be that there is underdetermination, there is some kind of underdetermination, but it is benign, and it is not a threat to a cautious scientific realism. And I will make clear what I mean by cautious. It means a scientific realism that first analyzes the import of dualities before making ontological comment. So it's closely related to what we discussed before. Okay, so what do we mean by empirical underdetermination? It is the usual notion. It is empirically equivalent theories that are nevertheless theoretically inequivalent. That's the notion of empirical underdetermination. So two models, in our sense, they are underdetermined if they are empirically equivalent, but theoretically inequivalent. What do we mean by empirical equivalent? Well, I think I will go into that. Notice, by the way, that in some sense, the discussion of underdetermination is orthogonal to our previous discussion of theoretical equivalence, because for theoretical equivalence, we reached a verdict of theoretical equivalence by considering internal interpretations. So interpretations that map dual models to the same domain, while for empirical underdetermination, we are interested in inequivalent models, and therefore external interpretations will play a special role. Okay, here are some words about scientific realism, but I think that is quite familiar what I have to say there. So then what do we need by this notion of caution? So we require a reading of a scientific theory that is as literal as possible, and this literality, this goes back to the discussion by Van Fraassen, which I skipped. So a reading that is as literal as possible, but nevertheless cautious, i.e. informed by foundational work, current scientific practice, and history. Again, this is not something new. This is not something that is prompted by dualities. This is what we always do. When we develop any kind of scientific realism, we take into account what is the kinematics of the theory, what is the dynamics, what is the state of what is the space of states, what are the quantities, and so on and so forth. So naturally, if we want to develop scientific realism, we also must take into account the fact of dualities. So a cautious scientific realist will suspend judgment about the existence of the positive entities until further interpretative work has been carried out that justifies the corresponding belief. So my critique by Van Fraassen here would be that he emphasizes, by emphasizing the literal reading, that can be naive in the sense that we never do a literal reading in the strict sense. We always, interpretation is always a combination of reading the theory with foundational work. And it's not any different for dualities. Selective scientific realist views are of this type. They are cautious because they assign reference only to those entities that played an important role in bringing about the effects that one is studying. So there is already quite a tradition and a list of types of scientific realists that are cautious. Okay, so now we can then come to the question of underdetermination. Do dualities be a case of empirical underdetermination? The answer to this is not immediately yes, because underdetermination requires empirical equivalence, while most dualities appear to relate empirically inequivalent situations. So this is a prior step that I'm not going to emphasize. It's something slightly technical. What I'm doing here in this dialectic is that I am giving my opponent, anti-realist, the benefit of the doubt. So I'm giving my opponent as many tools as possible so that they can develop their anti-realist case. If I am too strict about the notion of empirical equivalence, then the realist will win the case anyway. So that would not be a fair way to conduct the argument. So therefore, methodologically, I'm going to allow the anti-realist to be rather liberal about their notion of equivalence. That's all that I'm saying in this slide here. So with that side comment, here is then Libby and Reed's discussion of underdetermination. They give a taxonomy of possible interpretations of dualities. So we have two columns, we have T1 and T2, two models in my language, two dual models, and then here below, so the green and the red balloons, they are possible worlds. There are 6 possible worlds where the theory could be either true or false. Then they consider, in addition to this, they consider what we have called the common core approach. So basically this idea of internal interpretation, that you take only the common structure, the isomorphic structure, and take that as what you interpret. So this T in here in the third column, that is our, in my language, that would be my common core theory on which I apply an internal interpretation. Okay, so now they argue. Now they go through all the logical possibilities for each of these worlds, and you could have as many worlds as you want, but they limit it to the minimum number that you need. So they say, well, the theories could be both true, or they could be one true and the other false, or they could be both false on these worlds. And then, in addition to that, we could so this has 3 choices, 3 possibilities. In addition to that, we have this common core theory that gives us, that multiplies by 2, because each of them, the common core theory, can be either true or false. Then, so where I have written common core is basically the odd cases where the common core theory is true. So where I have listed common core, that's where the common core theory is true. They have these other approaches that they call discrimination of nihilism. I'm not going to focus on those because I'm interested in the common core approach. And then they conclude, well, we have 3 cases of underdetermination, because what is underdetermination here? Where underdetermination basically comes down to a statement that we have more than one green dot on the horizontal, right? So the first 3 cases, we have 2 or 3 green dots. Those are cases of underdetermination. And you see, if we didn't have the common core theory, we would actually be fine. Because we would, well, or we might not be as bad, because we would still have underdetermination, but only one case of underdetermination. By adding this common core theory, they argue, we have made the underdetermination even worse, because now we have 2 other cases where we can have underdetermination. So now we have 3 cases of underdetermination. So we have made matters worse by adding this idea of the common core theory. So those are basically the logical possibilities that we have just by counting, sheer counting of possibilities. Okay. Yeah, this is basically just explaining what I just did. Yeah. Well, also specifying that I'm going in my discussion here. I mean, one could discuss this in general, and like I said, of course, there might be some cases of underdetermination, but the interesting ones for us, for the question of scientific realism, is the case of unextendable theories, because we want to be cautious scientific realism. So I'm going to focus on those. And like I said before, we are also going to focus on the common core theory case. Okay, so what I want to argue is that the remaining cases that we get after these considerations are actually benign cases of underdetermination. They are not a threat to scientific realism. And that is because I would like to argue that internal interpretations are favored on logical grounds. So if we are confronted with a case of dualities and a potential underdetermination, nevertheless, we have logical grounds to prefer the internal interpretation. Let's look at how we defined the internal interpretation. We said we construct it by normally either by abstraction or by augmentation. So by crossing out the structure that is not common between the two modes, or by adding some items that are allowed by the model, adding those to our interpretation. So in both cases, both in abstraction and augmentation, the interpretation of the common core theory actually agrees with the interpretation of the two duals. So this is a very important point, which in my opinion, Levihan and Reed overlook. I think for understandable reasons, because they are not specifically discussing this case of internal interpretation, so they have just, they simply count the possibilities. But if we focus on the question of a cautious scientific realist, which is the sensible scientific realist case anyway, then we want to focus the discussion on internal interpretations, and then we need to take into account how internal interpretations are logically connected with the interpretations of the models, and this could be external interpretations of the models that we began with. So to write it formally here, the two models normally contradict one another. If one model is true, the other model is false. At least I said the dialectic in this way. Jeremy will have more to say about this from his own work on this point. So I'm going to say that the two models contradict one another. That is basically what we see here on the slide, right? So one model is true and the other model is false. That's basically what we need. Now, whenever the dual models are true, the common core theory is also true. So the common core theory comes out to be true if either M1 or M2 is true. So we don't need to know which of M1 or M2 is true. Or it is not even necessary that, you know, that one of them should be even true. So two representations of, for example, two representations of a group satisfy the abstract axioms that define that group, because representations are homomorphisms, and thus make the group actions true. So that's the sense in which I mean this, right? If we have models that are true on a particular world, then automatically the more abstract model will also be true. And also the model that has been augmented will also be true for the same reason. So out of the three candidate models, M1, M2, and T. So remember, Levihan and Reed's argument is, well, you've made the underdetermination worse by adding this common core theory. My argument is no, but out of these three candidate models, the common core theory is preferred because it is true in more cases. It is implied by the other two. It is always true if M1 or M2 are true. So scientific realism does not and cannot commit one to either M1 or M2, but commitment to T is justified given either M1 or M2. So I would argue that it is, one should not saddle the realist with beliefs in these other models if we know that there is a duality. So if we know that there is a duality, or if there is a duality, then we don't have epistemic grounds, good epistemic grounds. We are not justified in being realists about those models until we have carried out this kind of analysis. So cautious scientific realism takes duality as a starting point to determine realist commitments, as we always do in any kind of mathematical physics project or interpretative project about mathematical physics. Okay, so to summarize, theoretical equivalence, duality has a few things to say about that. Duality gives us a natural formal criterion of equivalence that is appropriate in physics because it is adapted to all these examples. There is a natural distinction between internal and external interpretations that is made by the schema for dualities, and also duality itself also suggests this notion of, or this contrast between internal versus external interpretation. There's also a natural meshing condition, a commuting diagram of maps that expresses the theoretical equivalence of duals, as we saw. So there is a way to formalize what we mean by theoretical equivalence, how that interpretative notion should match with our notion of isomorphism. We have seen that we have discussed the epistemic justification for verdicts of theoretical equivalence. I gave two conditions that are sufficient to make these kinds of verdicts, and the conditions were extendability and defining domains. I also endorsed the related motivational disposition of Reed and Miller-Nielsen. And then in the last part, I argued that dualities give no new ammunition to the anti-realist because the anti-realist should not, sorry, the realist should not be saddled with beliefs that they are actually not justified to having as cautious realists. Rather, but on the other hand, dualities do bear on the debate by suggesting this methodology of cautious scientific realism, which I want to emphasize is not something that is specific to dualities, but it's something that we do all the time. That any realist in their right mind would apply. Internal interpretations are favored by the logical relations between models. So even though sheer counting of possibilities might lead us to empirical underdetermination, if we look at the cases that are really significant for the discussion of scientific realism, and particularly of cautious scientific realism, then that discussion very much reduces the number of cases, because we need to take into account this logical relation, in particular the roles of abstraction and augmentation in internal interpretation. So dualities then are not only principles of individuation in this particular sense, in the sense that they combined with these interpretative tools that we have developed, we really have a good notion of individuation of models here. but they are also, they should be taken as a starting point of ontological commitment. So we shouldn't make our ontological commitments until we have worked out the details about the dualities and also apply these notions of internal interpretation. All right. That's it. Okay.
Thanks. So I guess we can have a lengthy discussion today.
Okay.
Does anyone have a question?
Paid online.
Oh, Twitter online is a question. That's that.
Yeah, well, actually, I would like because I mean, if you can give a working example, because I'm afraid that I'll be at a loss right now with this bunch of definitions, and of course it's a matter just of sitting down and digest the concepts, but because it has to do with basically my question yesterday on Monday on basically this ontological commitment that you've been emphasizing now in dualities. So, well, whether you can give taking even the basic example of Sain-Gordon theory model duality there, I mean, just to see this theoretical equivalence, empirical equivalence at work, because I'm afraid that a bit, yeah, well, otherwise just point to me, I mean, some references.
Yeah, very good. Yes, so I'm happy to discuss that more. So in this example that you mentioned, personalization, we discussed it a little bit the first day already, or at least there were some suggestions there. So the idea is that we have these two models. One is, so what I call the external interpretation is the interpretation where we say, well, the bosonic model is really a model about bosons, and we have some preconceived notion of what a boson is. While the other model, the competing model, is the fermionic model, is really a model about fermions. So, and we have again some historical notion about what a fermion should be. So those are the usual external interpretations. So the natural ones that we start with, the ones that have been given to us by history. Now we discover that there is a duality. We discover some formal relationship. So we discovered this first step of theoretical equivalence, where we have this formal relation between them. Now we say, okay, let's see if these theories are really theoretically equivalent. What would it take for the two theories, if it is the case that they are dual, what would it take for them to be theoretically equivalent, right? So we need to make the second step, the interpretative step of what is the interpretation that allows us to say with confidence, yes, these things are, these things are theoretically equivalent, in the sense of they are really the same. So they are two formulations or two descriptions of the same reality, the same domain in the world, because in the end, that's what the question of theoretical equivalence comes down to. So then we begin to work out this internal interpretation. And what does the internal interpretation in this case look like for us? Well, we begin from the common structure. So the common structure is this set of states we have, and this set of quantities. The set of quantities is the algebra, the affine Virasoro algebra that we discussed. So those are our quantities. And now these quantities, they are common to the models, but sometimes they interpret them rather differently. So now we're going to say, well, what is common about those interpretations? And in fact, there is quite a bit that is common about the two. So for example, if you take the Hamiltonian is common between the two theories. The only difference is that in one case it is formulated in terms of the boson, in the other case, the other case in terms formulated in terms of the Fermi. So now, in our internal interpretation, we are going to say this is just our energy operator. So this is the operator that gives us the energy of the system. That's our internal interpretation. That's the interpretation that is common to the two. We can do this for more quantities. So we're going to, so from that specific interpretation, we're not going to say, you know, this is the Hamiltonian for example, for a boson. We're not going to say that. We're simply going to say this is the Hamiltonian for our excitation, our physical excitation of this model. Now we do this for all the quantities, then we do that also for the states. When you do that for the states, then you also say something about what those excitations are. We said something about that already on Monday. So rather than using the notion of a particle versus a soliton, right? So that would also be a problematic notion that is not invariant under the duality, saying that this is a fundamental particle or saying that this is a composite particle. Those are problematic notions. So rather we're going to say that something along the lines of, well, the fundamental degrees of freedom of this theory that describe the physical excitations, they are, for example, the given, so that the states corresponding to those are the, you know, the space of highest weight representations of this affine algebra, and so on. So in this case, I mean, it's a lot of words. Sorry about that, but you can, in this way, you can see how you could build a whole interpretation where you have familiar notions like energy, angular momentum, spin, state of your system, and all of that. You can still work with those notions, but you don't need to include the problematic notions like elementary or composite or soliton or things like that. And so that's how you now have, so after you do this exercise, you have now constructed an internal interpretation. You have an interpretation that in some sense works for the two models. Now you don't really care which model you choose. You can use the two interchangeably. It's like, now we can really say these are like, you know, this is like a Fourier transformation, really. This is just like saying these are representations of, in fact, the same thing. So when you think about the Fourier transformation, whether we talk about X or about P, that's a choice in our representation. So quite similarly, in this case, we have developed that internal interpretation. And now we can say these two formulations are formulations of the same theory. They are representations of that model, and the internal interpretation is completely commutes with the duality. So now we, and yeah, and then you could try to apply the other notions of, you know, an extendability. So how do we justify that this is actually a good notion? This internal interpretation we could construct it as a good notion that, you know, that it will not be superseded by further knowledge, and that's where you have to do these additionals. But maybe for the sake of the discussion, I mean, I'm happy to fill in more about the details that I just discussed, but I don't want to talk too much. So I think there are also some other questions. I see some hands raised, but I leave it up to our chairman to.
So Michael, then Alexander, then.
Can the chairman also see the screen? Can you see who is?
No, I cannot see who is.
You cannot see that. Then, yes, okay, then.
You can keep track of that, yes. Please.
Yeah, I have also personally.
Yes, okay, fine. Thank you very much, Sebastian. Usefully clear and yeah, fascinating talk. I just want to ask a little bit about our actual meshing, which conveys a very strong category for every trailer. You've actually mentioned that using diagram and maps. Can you say a little bit more about that? I mean, is there a specific characterization of that condition, perhaps connected with the behavior of covariant reality of the maps that were stated? Has anybody looked at that?
Yeah, so there is, I can refer you here to Weatherall's paper. So there's a paper by Weatherall in that he gave at the PSA 2018 PSA, where he defined a functor between two categories, and he also defined a commuting diagram that had precisely this kind of flavor. So I could refer you to that paper.
And I do document also reply to that paper commented on it. There is already a literature stemming from that paper. Yeah.
Okay, thank you. Yeah, I would be interested.
Okay.
I'm wondering about the status of Hodge duality in electromagnetism in the following sense. So there's a kind of ideal vacuum case that's trivially and indeed uninterestingly dual, and that may be the case that one usually has in mind. But in fact, so what I mean specifically is between electromagnetism and magnetoelectrism, between the Faraday two-form and the whatever it's called, two-form Maxwell. So I think the specific Hodge duality one usually has in mind is physically empty. But of course, it isn't in fact, because in the background are constitutive relations, the properties of the medium, space-time curvature, or non-trivial epsilon, mu, by epsilon I mean the dielectric tensor, or mu, the magnetic, what's it called?
Permeability.
Exactly, magnetic permeability. Those in general aren't even scalars. I mean, so that's in fact what's at issue in the Hodge duality between those two forms. Do you feel like saying something about that?
Yeah. So that's interesting. So there are two things one could say. Sometimes, actually, Weatherall also talks about this in that same paper. One could ask, well, is this electric magnetic duality, is that so surprising? One could argue, well, in some sense, we already know from special relativity that there is some sense in which electric effects can become magnetic effects and vice versa. So we can create, starting with a non-zero magnetic field, we can create, starting from a zero magnetic field, we can create a non-zero magnetic field by going to a moving frame and so on. So we already know from special relativity that there is some relation, some relation that we expect between electricity and magnetism, purely in terms of the fields, purely in terms of the electromagnetic fields. However, I think that there is a surprising element an important element about electromagnetic duality, which is when we consider these external interpretations, when we say, well, how do I define electric and magnetic? What is an electric field? In particular, a physicist would ask, how do you measure it, right? You usually do that, you will do that, for example, by some test particle, putting a test particle in an electric field. The kind of physical setup that you need for that is different from the one that you need to measure a magnetic field, because to measure a magnetic field, you will do an induction experiment. So so it is not like Einstein had a very clever way to argue that, no, my electric situation and my magnetic situation are dual, because even the measurings of those things I can match through my special relativity. I would argue that we cannot do that with the definition of the electric and magnetic fields themselves in what we call an external interpretation. Because external interpretation will say, well, what I call electric is basically the response of a certain type of particle to an electric field. So that's why it is an external interpretation. It uses some external notion that is not there in the theory, but that nevertheless is needed to give a substantive account of what I mean by electric as opposed to magnetic.
Well, the so Faraday is electromagnetism, and the other one is magnetoelectrism.
Magneto. Okay, so he argues that those are equivalent for that reason, because he has this forgetful phantom, and he argues, well, these two theories are empirically equivalent, so this is just what we expect. I know I have empirical equivalence. I can construct such a functor, therefore it should just be the same. That's where I would say that's too quick for me, because these are, again, because these are external interpretations. So if you it may be that these theories are equivalent at the level that Weatherall discusses them, but the extensions are not. So the only way, for example, to include monopoles is to have the gauge field rather than the electric and the is to have the the only way to have extensions of this field, for example, coupling to other fields in quantum field theory, or even describing things like the Aharonov-Bohm effect, is by including the gauge field. So even though at the minimal level of this particular theory they are the same, but it doesn't satisfy my unextendability requirement. So unextendability would say you can extend these two formulations in different ways, and therefore I should be cautious before I say that they are always theoretically equivalent.
Thanks.
So
if you could solve that problem on the line. Yes. So are there questions on the line? No.
I can have something maybe.
You want to ask? Otherwise,
Naive question. So, according to the common core interpretation that you explained before about personalization, no? I was thinking about open-close duality. Then you would say something like, I mean, the theory is not a theory of string and brains, but there are, I mean, excitation of, what would you say there?
Yeah, that's a good one. I mean, part of the problem is that in string theory, we don't actually know whether it is going to be an exact theory. But I can say, well, let me give you an answer that I personally disagree with, but that is in the literature and that I think gives insight into how we go about this. So Horowitz and Polchinski, in a paper that I think I will quote it tomorrow, they argue that that type 2B string theory, including its D-branes and ADS, that is simply n equals 4 superdiagonal theory. So he says, in the end, the lesson about ADS-CFT is that string theory just is a gauge theory. I personally, I tend to disagree with that. I don't think there is enough evidence to think that, and in fact, there are programs that. But okay, let's assume that as a kind of technical assumption. Now, if you go with that, then you would say, "Oh, nice." So apparently, they are telling us that really the common core theory of ADS-CFT is just this theory that is living at the boundary. So we always thought that string theory was something about, was a theory about space-time, about solutions of general relativity and so on. Now we learn that if we want in particular to construct, and I have argued this in a paper, if you want to actually construct this triple for ADS-CFT, you should not look at the space-times of general relativity. That's not the set of states and the set of quantities. Rather, you should look at the conformal structure at infinity. So where this theory is really living is at the boundary of ADS-CFT. And this might be a movable boundary if it is a theory that has renormalization group flow. So there might be some parameter, but there is some sense in what, kind of the common core of ADS-CFT is this kind of structure that's completely different from how we normally learn about ADS-CFT. And I think that could be the case in other cases for the D-branes. Well, that would require more work and knowledge. I think that's an open question for people who are interested in this kind of work to really look into that. What do we really learn from these dualities about the degrees of freedom of string theory?
Yeah, the second question is even more naive, maybe. So in the first day, when you were explaining your schema, you were saying that the theory is a model, and then you have also the structure, right? The model structure, right? And I was thinking about that in the example you gave for quantum mechanics, right? You said that you have the state that can be represented both in position and momentum space. No? And these are two models that are dual to each other. So the X and the P are the structure, right there. So I was thinking that there should be some compatibility condition between the structures themselves, because otherwise, the two models are not related by a duality, or in that case, because the Fourier transform heavily depends on the compatibility between X and P on the Heisenberg algebra, basically. Yeah. So I was thinking about that, and I was thinking about a more sophisticated example, bosonization and so on, and it was difficult to me to match what is the model structure and how we are asking for compatibility conditions between model structure and so on and so forth. I don't know if you can comment about it. or if it is, I mean, a strange point of view on your schema.
Yeah, so I mean, let me see. Yeah, so it's one way to think about this would be that, I mean, we said sometimes we abstract, so we write down a theory that is more abstract and has fewer variables. That's what we do when we write down the Hilbert space formalism without the choice of basis. And that might be enough to do quantum mechanics. But then, yeah, if we want to do like practical calculations, then we need to choose a basis. And this is something that also, it's somewhat analogous to when we deal with manifolds. We have an abstract manifold, and we have a topology in it. But then, if we want to do specific calculations, then and we have these maps to Haro and so on, we need to do specific calculations. Then we need to actually make a choice of basis. So I think it is analogous to that. We add some additional. That is the additional structure that we add. It doesn't mean that it's irrelevant or that it's not there. It's just structure that we add to the model to be able to use it as a sample. To do practical calculations. And I mean, and yeah, I would say that the duality transformation itself is a compatibility condition. It's a condition that the Fourier transformation is a compatibility condition. It tells you, well, everything that I can, if I choose a basis, that's fine, but everything that I do with that basis, I should be able to do with the other. What the internal interpretation says is that, okay, you have that structure, it's not common, but it's there. I'm just not going to interpret it as such. I'm not going to interpret it as a specific structure. And that will depend on the case. In some other cases, so that's for the case of quantum mechanics. And in the case of Bosonization, I argued, so this is a case of abstraction. In the case of Bosonization, I argued it looked like it goes in the other direction. You want to, I mean, the structure was already there from the beginning. I didn't need to add them because there were already operators, regardless of representation, there were already operators there that are these exponentials. And so those I need to basically include that. So augment my interpretation. So what I would say is that duality is the compatibility condition for the different models. And so the relations between the models that you have, in other cases, there will be mere representation. So there will be only a homomorphism, there will not be an isomorphism. But if there is an isomorphism, then it has to be consistent.
So back to the question.
Thank you a lot for the clear book. I just have one curiosity. So, as you know, in the literature on underdetermination, there is an epistemological question concerning how we recognize whether the equivalence is genuine or fictional.
Actually, whether
the equivalence between theories is genuine or just fictional. For some example of apparent genuine equivalence, say Wolfram Gertani's quantum mechanics, though they are not really equivalents. And purely by logically speaking, equivalent theories, whether one of the theories is not really a scientific theory. So like Newtonian mechanics and Newtonian mechanics plus the claim that one exists. They are empirically equivalent, and they're not theoretically equivalent. And of course, philosophers consider this second classification irrelevant whatsoever. But my question is, given a model in your language of a theory, is it always possible to build a dual of it inside the theory? And I mean, the reason why I ask is if that is the case, then it raises some question about how do we reckon whether the duality is genuine, and we should be ontologically committed only to the concept, or whether one is just a mathematical stuff and the other is ontologically pursued.
Okay, I'm not sure. So I see different parts of the question. I'm not sure I fit them together yet, but so I can try to say something about the first part of the question, which was about if you have two duals. At least if I repeat it correctly. So if you have two duals, you could have an interpretation where one is a scientific theory and the other is not a scientific theory because you make some additional assumption, like I have angels on the hair of on the tip of my hair or something like that. So how do we distinguish about between these cases? Actually, there is a recent paper, I forget the name of the author, about just this kind of case. What this author says is that basically, so he says that formal projects are completely irrelevant for the project of theoretical equivalence, because he says you can always do this kind of thing. Any interpretation that you have, you can always add some additional thing that you cannot check, and then the duality is broken. I profoundly disagree. I mean, I disagree with that because so his argument seems to be. So he says you can represent. So anything can be represented by anything, basically. So if I have the letter A, that can represent the theory of everything. And so regardless, or A equals B, so regardless what my formalism is, the semantics could be arbitrary. And so my whole theory of everything could be encoded in something quite trivial. So I think this misses the point of that the semantics is not arbitrary, and you can compare interpretations with each other, and that's precisely what we do when we have duals. We say, well, theories have certain descriptive capacities. They have states and quantities, and we have dualities between them. So depending on those capacities, I can afford one interpretation or the other. So it is not. So dualities are not irrelevant. Still, there is a point you can always add something extra. But that, for me, that just falls under what we call external interpretations. So those, and that's fine. I mean, I can never exclude that. And this author gives the example of panpsychism to kind of make it semi-scientific. He says we could, we could ascribe some mental properties to elementary particles, for example. And then how do we know? How do we distinguish those two? I would say that just falls under the external interpretation. So on an internal interpretation, those additional properties are simply not there. So we don't need to interpret them, to include them into our interpretation. So that's why I said internal interpretations are sufficient, together with these other conditions, are sufficient conditions for duality. Second part of, but I don't know if there are.
No. Okay. So the second part is just a general question about if you are model of achieving. So always is it always possible to be that dual model in the same field?
Oh, you mean formally?
Yeah.
Or? I guess that. I mean, I don't think. I'm not sure if there is a general answer to that. I guess you can always find some kind of clever or very trivial, maybe, isomorphism. I mean, the identity is already an isomorphism, so in that very trivial sense, but that's not what you are asking. Of course, you're asking whether there is always some interesting isomorphism that you can come up with that has like a physical meaning. I don't think there's a general answer to that.
So I lose my sharing my privileges, and I wanted to ask something. So, since before you were talking about interpretation of ADS-CFT with Marco, and it seems that this Wojcinski interpretation that you were discussing is some kind of extreme application of what you call the abstractions principle approach to constructing the common. And so maybe let's split the question in two parts. So the first part was whether you have any thoughts on how an interpretation of the CFT that relies on the augmentation principle might work. And here what I had in mind was something like, okay, maybe we could, on the CFT side, looking in the non-perturbative sector arbitrary, we might find some sort of perturbative subgroup that looks like a classical gravitational solution, which is what I think up as duality, something like that. So that is maybe the first part. If you have any thoughts on that and how it might look, and especially in terms of like ontology and interpretation, and then maybe building on that, whether you have any thoughts on the question of whether there are in general principles that might tell us when we are given some sort of duality, whether it is better to use the abstractionist approach to its interpretation or the augmentation approach to its interpretation, or whether we can mix and match. I don't know, like are there general principles governing which approach we should use, or it's just we try them all and we see which is the most satisfactory.
Yeah, it's a good point. I think one interesting way to look at this could be to augment as much as possible. So to take as much common structure as possible, right? Because if you have two duals and they have common structure, you are able to encompass it through the duality, then maybe you should include it. So in the case of ADS-CFT, so I would say abstraction, I think, at least from a physical perspective, of course, you can have different interests, why you want to build these common core theories, but from the interest of physics, of being able to interpret and do calculations and make predictions, I think as little as possible abstraction is good, because then you preserve as much structure as possible. So that gives you kind of computing power. In the case of ADS-CFT, I mean, there is this idea that people say the bulk is not there because everything is on the boundary. So the theory is really defined on the boundary. But of course, in some sense, I mean, the boundary is only the infrared limit of the, or sorry, I should say depending how you look, the ultraviolet limit from the boundary perspective. So it is a specific limit of the boundary theory, but the boundary theory, of course, depends itself on at least on the Wilsonian approach, on an extra scale, a cutoff scale, which matches. I mean, it's true that we don't have a detailed map of that with the of the renormalization group direction with the radial direction. So kind of, on a loose talk, we could say, yes, walking in the space of theories, in the space of Wilsonian theories, that is the same as walking inside the ADS space. But of course, we don't have like an explicit map. And that is what some people do refer to the JT theory, one of the cases where they can actually do that. And also Wojcinski and others had some papers about that around 2010. And I think there is also work by Day, where in a different context of gauge theories, where it tries to do that. So yeah, I think attempts to do that would be very beneficial, because then basically you can expand or augment what is your common structure. And the only thing that it would, then the question becomes, what will be the interpretation of that extra dimension? It's clear that it will not be as a spatial dimension, simply because that is not common to the two. Okay.
Well, I'll also follow up that. Okay, you just mentioned. No, because what you said about augmenting as much as possible was very interesting. But I mean, now I'm kind of worried that that kind of contrast with your argument regarding the empirical underdetermination and why dualities do not give cases of empirical underdetermination. Because what you said there is that you can take the two, let's call them local interpretations, external, I think should work, interpretations. You're like, well, either one is true or the other is not. And while the common core interpretation is true in both cases, so it's better to use that. But now I could maybe run the same argument if we augment as much as we can. So I could take an augmented interpretation. I could take a maybe slightly less augmented interpretation. And then I could take a third one, which is even less augmented, and I could claim, assuming that we preserve at least the empirical information, that the less augmented theory is actually the one that is the most parsimonious, and that any further augmentation gives me a theory that is true whenever my more cut theory is true, but that there is going to be at least, maybe there might not be a case where they're actually not true, but one is at least more parsimonious, and presumably I might someday find some case where that less mathematics than I'm assuming allows me to say to actually accommodate some case that I didn't have. So couldn't one try to basically adapt the argument that you gave against the underdetermination, try to be cautious realist, to say that you should actually augment as little as you can, preserving empirical information at least.
Well, that argument was in the case where these theories disagree with each other, where the two theories or they contradict one another. But my assumption, I mean, the assumption of the starting assumption of the discussion was that we're still trying to build an internal interpretation. So if I augment, but then I am not able to find an internal interpretation, then I would agree that would not be good. So by what I mean by augmentation is part of the process. It's not a formal process, but it is part of the process of building my internal interpretation. So I take, so the structure is already there. I don't change the structure. What I do is I simply rebrand rebrand my structure as being physical or not. So if I'm able to take structure that goes through the two interpretations and still get an honest, a good internal interpretation, then I would argue that is, and in particular, an interpretation that still agrees with either of the two. Then we are still fine. So what in other words, I mean, you could have like the same puzzle if you say, okay, I begin with a theory, I have a particular interpretation, it's an internal interpretation, and now I start to drop things from the interpretation. Does that give me underdetermination? I would say, well, that is not a cautious way to proceed, because I am simply ignoring stuff that is there in the theory and for which there exists a good internal interpretation. Yeah, I mean, yeah.
So it's about one should try to put as many stuff as one can into the interpretation, as long as it remains internal, basically.
Exactly. Yeah. So the key thing is it should be internal. Yeah, and then indeed it's a matter of discovering what is really the duality source, and that can be empirical work. What is really the content of the duality, and what does it relate between the theories? So that's something formal that it's a formal project that one needs to do before one can do this internal interpretation.